Good morning, everyone. You're all doing well. So we're going to finish up here with chapter 8, which is the last chapter of for your third test, which is this Sunday, Monday. This test, I think is the most challenging of the 3 tests or the 4 tests, just mainly because there's so much math involved in it. People tend to like shy away from math. But make sure you're using your notes, make sure you know your systems, what you want to use when and where, and I think you will be able to get through it. So this next chapter here is going to be pretty much combining the last 2 chapters into one big sort of amalgamation. So we had all those calculations where we were talking about like grams to moles to grams, and then we spent a bunch of time balancing equations. Well, now we're going to look at how a balanced equation is actually also a molar relationship. So chapter 8, quantities in chemical reactions. All right. Global warming, too much carbon dioxide. So when we combust fossil fuels, which you guys should know now because of your understanding of a combustion reaction, what is produced is water and carbon dioxide. Now, carbon dioxide is a greenhouse gas, which means that it helps to hold in or absorb the sun's radiation. So it looks something like this. We get visible light coming in, and that light will get absorbed by the earth, and then it reflects back off of the earth. And some of that heat is released back out into space. But the thicker that our ozone is and the thicker that these greenhouse gases are, the less heat that can be released from our atmosphere. And so the heat will then sink back into the earth. And if this happens enough, you'll actually start to get an increase in temperature at the surface of the earth, which is what we're seeing right now. There's a lot of secondary effects to that outside of just an increase in temperature. You start to see ice sheets melting. You start to see increased storm patterns, increased droughts, all sorts of horrible things. So where the CO2 is coming from is a lot of it is coming from the combustion of fossil fuels. So we use fossil fuels not just to drive our cars. I mean, we use fossil fuels to produce all of the products that we use. You know, the t-shirt that you're wearing has a carbon footprint to it that has used a certain amount of fossil fuels to be produced. If we're talking just about the combustion of octane, which is what we put in our car, here's octane, C8H18. Again, I don't expect you to know the names of these, like octane being this. I would give that to you because that's organic naming, which is a whole other beast of nomenclature. But what we find is that 2 of these octanes come together with 25 oxygens, and look at that, bam, you get from 2 octanes, you get 16 CO2 molecules. So that's a huge ratio, right? So for every 2 jumping ahead. So for every 2 of these molecules, we get 16 of these molecules. Now remember, a molecule relationship is the same thing as a mole relationship. So we can also say that for every 2 moles of octane burned, 16 moles of CO2 are burned. Okay, so these coefficients that sit in the front create a mole relationship between compounds. And they're very specific to this form or this chemical reaction. So for combusting octane, this is its signature recipe. So let's take it a step back and talk about recipes. Well, let's talk, what was that I just talked about first? That thing is called stoichiometry. And so stoichiometry is a relationship between ingredients. It's the numerical relationship between chemical quantities within a balanced chemical equation. So if you have a balanced chemical equation, meaning you've got the correct coefficients, everything is nice and neat, same atoms on both sides, you can actually say that a certain number of moles of one thing is equivalent to a certain number of moles of another thing. So that means I could say, hey, I have 55 grams of octane. How much CO2 is going to get produced? And you can come up with that answer because you can predict the certain amount of products if you're given a certain amount of reactant. You can also predict how much reactant you would need if there was a certain amount of product that you desired. And you can also jump from one reactant to another reactant. So, hey, if I've got, 55 grams of methane, or rather, let's go with octane, 55 grams of octane, go back here. How many grams of oxygen do I need to combust with that? This is all built into this recipe. So we're going to bake first. I'm sure that you guys have all looked at a recipe before. This recipe is for pancakes. And what you notice here is that there's a number in front of each of the ingredients and the resulting product. So we don't just say, hey, flour plus egg plus baking powder equals pancake, right? There's a lot of options there. How much flour do you need? How many eggs do you need so that you can get that perfect pancake? So think of the numbers sitting in the front here like the coefficients of a balanced chemical equation. For every 1 cup of flour, you can have 5 pancakes, right? For every 2 eggs, you can produce 5 pancakes. For every half teaspoon of baking powder, you can produce 5 pancakes. Well, anytime you've got these equalities, you have conversion factors. So we're back to dimensional analysis. So let's look at a simple one here, 2 eggs and its relationship to pancakes. So for every 2 eggs, you can get 5 pancakes. A ratio for that would look something like that. 2 eggs to 5 pancakes, right? Or we could say 5 eggs needs 2 pancakes. Now, what if you're in a situation where you have 8 eggs? You go to you're gonna, bake some pancakes and you have 8 eggs in the fridge and you have a plethora of everything else. So you've got like 100 pounds of flour and more baking powder than you could, ever need. Well, what is limiting the reaction is the eggs, right? Because you have an excess of the other stuff. So we need to figure out how many pancakes the 8 eggs can make. So I take my 8 eggs, I use my conversion factor, which says 5 pancakes for every 2 eggs, right? The eggs will cancel. 8 times the 5 divided by the 2, you get 20 pancakes. So 8 eggs can produce 20 pancakes. And you may be thinking, well, yeah, I could have done that in my head, right? If there's 8 eggs and you need 2 for every 5 and you carry the 1, whatever, you do it in your head. Well, I want you to set it up like this because this is how we're going to set it up when we're looking at the chemical formulas. So this is a balanced equation for the synthesis of ammonia. We have hydrogen combined with nitrogen to produce ammonia. Specifically, 3 hydrogen diatomics plus 1 nitrogen diatomic will produce 2 ammonias. Now, these coefficients are just like, and this is an inferred one here, are just like the numbers in the recipe, right? You had 2 eggs for every 5 pancakes. Well, here we have 3 of these hydrogens for every 2 of these ammonias. Now, this is not a mass relationship, okay? Not a mass relationship. So this isn't, 3 grams of hydrogen will produce 2 grams of ammonia. No. It is, once again, a mole relationship. Turkey, stop. Turkey, stop. Sorry, my French bulldog likes to catch ants off the floor. That's like one of his favorite things to do. So if you hear him shaking around, that's what he's doing. Keeps our house clean. All right, so let's look at some of these relationships. If you write them all just stitched together, it would be 3 of these for every 1 of these, for every 2 of these. They have it as molecules, but remember molecule and mole are equivalent to each other. So it's 3 moles of the hydrogen will produce or will need 1 mole of nitrogen to produce 2 moles of the final product. You guys see how that relates to the baking example? Where, these are just ingredients with their own set recipe, just like the pancake recipe had its own set recipe. So now we can use this relationship and go from one thing to another thing. Like I could go from the amount of moles of hydrogen to figure out the amount of moles of the product because it's a 3-to-2 ratio. So let's look at an example of this here. It says, hey, if we have 3 moles of nitrogen gas and more than enough hydrogen gas, anytime it says more than enough, it means you can just sort of ignore it, right? It's in excess, so we have enough of it. How much of the product can we make? So the two things that we're going to look at, we're looking at the nitrogen and we're looking at the product. This we can just sort of ignore. It's not coming into play. Now, it's important because it's required, you need that in order to balance the equation correctly, but for this specific problem, we don't have to take it into account. So now looking at the relationship, we get 2 moles of the product for every 1 mole of this specific reactant, nitrogen, 2 to 1. So we start with our given information like we always do in dimensional analysis, which is 3 moles of the nitrogen gas. We set up our conversion in such a way that the mole will go on the bottom, the mole of nitrogen will go on the bottom, and then the 2 moles of the product will go on the top. And these cancel, and we're left with 6 moles of the product. Just like when we converted from eggs to pancakes. So let's have you guys do one of those. Okay, so how many moles of aluminum are needed to produce 66.4 moles of aluminum oxide? And I'll give you the balanced equation. And this is important. You cannot do stoichiometry without a balanced equation. Like you can't bake without a recipe, right? So you need a balanced equation. So aluminum, I'll give it to you, plus oxygen will produce aluminum oxide. And I'm going to balance this out because we need the correct coefficients. So we'll put a 2 here, a 4 here, and a 3 here. This follows the same system as the last problem we just looked at on the slide, so you can use that as a model, and I will give you all 5 minutes to work through that. Okay, so for this one, we start, let's write out our given. We have 66.4 moles of the product, Al2O3, and we're trying to find moles of aluminum. So in this case, we're actually going from a known amount of this to a desired amount of a reactant. And you can totally do that. You can hop all around. So we're using this 2-to-4 ratio. We'll start with the 66.4 moles of the Al2O3. And we get, let's put the 4 moles of aluminum on top because that's what we want. And we want to get rid of the 2 moles of the Al2O3 so that those will cancel. Okay, it's just like the dimensional analysis we've been doing since the very beginning of class. Set it up so that the things you don't want cancel and the things you do want stay around, and then just follow the calculation. So 66.4, we'll multiply it by anything on the top, and we'll divide it by anything that's on the bottom, and we get 132.8, 3 sig figs, so 133 moles of aluminum. Okay. So is it making sense, these ratios? What's another ratio that you could use off of this equation or reaction? You could say, hey, 3 moles of oxygen will produce 2 moles of the product, right? That's another one that's built in there. And then you could also say, hey, 4 moles of aluminum will combine with 3 moles of oxygen, right? So you could jump between these two guys as well. So in real life, how often are you given moles? Never. What are you given things in? Grams. But hopefully now you can start to see that grams and moles are really interchangeable because as long as you know what the material is, you just use its molar mass. So this is going to be the flow chart that you follow for your stoichiometry every time. We've done this center part. I gave you moles of A and we went to moles of B. And when we say A and B, we just mean compound A and compound B. So we just did this problem here where we use the ratio from the balanced equation. That hops us between those two. But we're usually given things in grams. So the flow chart goes mass of A or grams of A into moles of A. Then from moles of A, we go into moles of B. And then moles of B, we go into mass of B. And we did a little bit of this in chapter 6 when we were going from the compound to the individual element amount, like how much sodium is in sodium chloride. We did grams to moles to grams because there was no direct way to go from gram to gram. That does not, nope, doesn't exist, okay? So we have to take a 3-stepper. Now, if you're in a situation like with that last problem where it gave you moles of one thing and it only wanted moles of another thing, well, you only have to do 1 step. So that's nice, but that's not always the case. So let's look at that same problem we were just working on, this one here. I'm going to change it up just a little bit. And I'll go through this one with you together. Well, we'll just erase the whole thing. We'll use the same balanced equation though. How many grams of Al2O3 are produced from 14.3 grams of O2 and excess aluminum. So we're going from grams of A, and grams of A is going to be our given, so grams of O2 into moles of O2. moles of O2 into moles of the product. And then moles of the product into grams of the product. Now, how do we get from this step here, grams of O2 into moles of O2? We need to use the molar mass of O2, but it's O2. So it's 2 oxygens. It's a diatomic. So the mass is not 16, it's 32 grams per mole. What is the ratio? Oh, let me put the balanced equation back up. 4 aluminum plus 3 O2 produces 2 Al, 2 O3. So the ratio between the oxygen and the product is a 3-to-2 ratio. 3 moles of O2 for 2 moles of the Al2O3. And then this last step here, well, we need the molar mass of aluminum oxide. Some people will say, well, should I double the molar mass of aluminum oxide because there's 2 here? No, you've taken into account the 2 here. So don't reapply it here, only do the mass of 1 molecule. So hello, Dr. Google. Aluminum oxide, molar mass. 101.96 grams per mole. Now, as you get better with this, you obviously don't have to like lay it out in so much detail, but I think this is helpful in the beginning to figure out what you're trying to do. So let's set it up. Start with our given, 14.3 grams of O2. From there, I want to convert it into moles. So for every 1 mole of O2, I have 32 grams of O2. Then from there, I want to go from moles. So we did this first hop. I want to go to the second hop where we go moles of the product. So moles of the product, moles of Al2O3, which gets a coefficient of 2 for every 3 moles of O2. All right, and then the last step, moles of the product into grams of the product. So 1 mole of the Al2O3 produces 101.96 grams of Al2O3. The grams of the oxygen cancel, the moles of the oxygen cancel, the moles of the product cancels, and we should just be left with grams of the product. And we plug it in. Might want to do the same thing just to make sure, plug it in, just make sure you're getting the right answer. So that 14.3 multiply by anything on the top, divided by 32, divided by 3, we get 30.4 grams of Al2O3. So if you have 14.3 grams of O2 and an abundance of aluminum, you can produce 30.4 grams of Al2O3. Any questions on that? Let's have you guys do one, okay? So we'll stick with this same formula, just make it easier, but let's change out the numbers. So how much oxygen is needed to combine with 187.1 grams of aluminum. And again, the formula is 4 aluminums plus 2 O2s produce 3 Al2O3s. Okay, so I'm going to give you all 5 to 7 minutes to work on that one. You can use the previous one as a skeleton structure for what you want to do. Okay, let's come back together. So this one is comparing two reactants to each other, two of the initial ingredients. So we're going to go from grams of the aluminum into moles of the aluminum into moles of the oxygen, and then moles of oxygen into grams of oxygen. 187.1 grams of aluminum. All right, we need to convert that into moles of aluminum. So 1 mole of aluminum is 26.98, right? Grams of aluminum. Pulling that out of memory here. Okay, so then we want to relate these two things to each other. So since aluminum is, moles of aluminum is up here, we're going to put the mole of aluminum down here. So 4 moles of aluminum for every 2 moles of the oxygen. Final step. For every 1 mole of O2, treat this as a packet. There's 2 of them. We get 32 grams of O2. Okay, your diatomics, you do need to take into account having 2 of them. And again, some people will say, well, but there's 2 of those, so shouldn't it be 64? No, you took the 2 into account in this middle step. You don't repeat that on the ends. The ends, right, the tails are 1 moles. The middle is where the coefficient goes. So we plug this in, 187.1 times 2 times 32 divided by 26.98 divided by 4. All right, we need 111.0 grams of O2 to combine with that much aluminum. Any questions on that? Okay, there's more to the chapter than this, but this is like the basis of it. So if you feel pretty comfortable with this, the rest of the chapter should kind of fly by. Well, not fly by, the problems take a while, but the concepts don't expand much farther than this. So we're going to talk about these different things with the recipe, with the pancake recipe. So there's a word called limiting reactant, theoretical yield, and percent yield. Okay, limiting reactant is the reactant that is holding back the reaction. Okay, it is the thing that is preventing you from producing more. Versus an excess reactant. An excess reactant would be something that you have an abundance of. There's more than enough of it. Golly, it'd be nice if you could make more, but you can't. The limiting reactant is holding you back. Okay, the theoretical yield is the amount that you could produce in theory if you ran the experiment perfectly. And then it's not on here, but there's another thing that's called actual yield. And we're going to go over all these. Actual yield is what you actually produce. Okay, so in theory, it'd be great if you made 55 grams of aluminum, but actually you maybe only made 53 grams. So the final thing here is percent yield. Percent yield is like how good were you at running the experiment. So you would take your actual divided by your theoretical and multiply it by 100. And again, we're going to go through all of this. So let's make some pancakes. Let's look at our recipe here. We've got a cup of flour for every 2 eggs and a half teaspoon of baking powder to produce 5 pancakes. Well, let's say that you go into your cupboard and you find that you have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. You've got some friends over and you want to make some pancakes. So you're going to figure out how many pancakes can I possibly make? Well, each of these things is speaking to a different number of pancakes you can make, right? 3 cups of flour, if we use our conversion factor, which says 1 cup of flour for 5 pancakes, 3 cups of flour could yield 15 pancakes. 10 eggs can make 25 pancakes, and 4 teaspoons of baking powder can make 40 pancakes. So the the limiting reactant here is going to be the flour. The theoretical yield is going to be 15 pancakes. Why can we only make 15 pancakes? Because we're held back by the amount of flour we have. And it's like, well, can't we make 40 pancakes because that's how much baking powder we have? Sure, but then you're just going to have a pancake that is mostly baking powder and doesn't have the right amounts of the other things. So we have enough flour for 15 pancakes. So how many pancakes can we make? 15 pancakes. It's our limiting reactant. So this is the limiting reactant. It's the material that's holding you back. It's not a number. The limiting reactant is the ingredient, material, compound that holds you back. The theoretical yield is how much does that limiting reactant produce. So it's the lowest of the 3 or the 2 or however many you calculate. Let's say, suppose that we cook our pancakes, so we can make 15 pancakes. Awesome. But suppose we cook our pancakes and we accidentally burn 3 of them and 1 falls on the floor. So even though we had enough flour to make 15 pancakes, we actually only made 11 pancakes. The 11 pancakes would be what's called the actual yield. Where does that come from, that number? I would have to give that to you or you would run it experimentally, right? The theoretical yield you figure out stoichiometrically. The actual yield is something that would have to be given to you. So how good were we at making pancakes? That's what the percent yield tells us. So percent yield is actual over theoretical, or percent yield. A comes before T in the alphabet. So A over T times 100. So with our percent yield, it's going to be the 11 pancakes over the 15 pancakes that we could have potentially made times 100, and we get an actual, or rather a percent yield of 73%. So you were 73% good enough at making pancakes. I don't know, burning 4 of 15 pancakes or ruining 4 of 15 pancakes. That seems like a high loss value. So does that make sense? Do those words and numbers make sense with the recipe? Like if I was to give you a pancake recipe, you'd be able to pick those numbers out. Well, let's apply it now to chemistry because I don't care about pancakes, but I do care about these sorts of concepts when we're looking at a balanced chemical equation. So I don't want to do this one. I've got my own that I want to do because in the slides for these, they mix it up somewhere. They mix the numbers up, yeah. So we're going to use a different one. Well, no, you know what? We're gonna do a different one, and then that one I'll have you guys work on. So I'll make one up that we can do together. So let's say we have the formula. Trying to think what I'm gonna do here. Okay, so calcium plus oxygen produces calcium oxide. Okay, so you have 14.3 grams of calcium and 19.4 grams of O2. What is the limiting reactant? and theoretical yields. So these two things we're gonna find out simultaneously. Just like when we were looking at the pancake recipe, you had to convert everything to the product, right? You had to take flour and convert it to the product. You had to take eggs and convert it to the product because we needed everything to be in the same compound. Like right now, this is in calcium and this is in O2. This is like apples and oranges. I need them both to be converted into the product. So that flow chart of stoichiometry of grams to moles to moles to grams, we get to do that 2 times. We have to do it for calcium. We need to get calcium over as a product, and we need to get oxygen over as a product. So let's start with calcium. I know that I have 14.3 grams of calcium. I need to convert this into moles. So for every 1 mole of calcium, it weighs, it's like 40 or 40.08. 40.08 grams of calcium. Now from there, I want to go from this into the product. So 1 mole of calcium, 2 moles of calcium will produce 2 moles of the calcium oxide. So from there, we now need to convert from moles of the product into grams of the product. So for every 1 mole of the calcium oxide, I have a mass of, let's see, 40 plus 16, 56.08 grams of calcium oxide. Grams of calcium will cancel, moles of calcium will cancel, and moles of calcium oxide will cancel. We end up with 20.0 grams of calcium oxide. Yay, we're done. Nope, not yet. We got to do that same thing with the other guy, right? This would be like us just figuring out what the flour can produce. We also have to figure out what the eggs can produce. So we're going to look at the other ingredient, which is the O2. We've got 19.4 grams of the O2. We want to convert that into moles. So 1 mole of O2 is equivalent to 32 grams of O2. All right, and then the ratio for that to get from O2 into the product is a 1, there's an inferred 1 to 2. So 1 mole of O2 will produce 2 moles of CaO. Last step is to get that into grams, and you already figured out the molar mass from the first one. So 1 mole of calcium oxide for 56.08 grams of calcium oxide. Grams will cancel, moles will cancel, moles of product will cancel. We'll be left with just grams. So. All right, and this says that we could produce 67.99. Okay, so I need to go with 68.0 grams of calcium oxide. So now it says, what's the limiting reactant? Well, what will produce less? Calcium. So calcium is the limiting reactant. What is the theoretical yield? This number over here, the lower of the two values. This is our theoretical yield. Say that this is part A. Let's do a part B. What is the percent yield if the actual yield is 16.4 grams of CaO? So remember, percent yield is equal to actual over theoretical times 100, or A over T. Here's the actual, it's given to me, 16.4 grams. Where is the theoretical? It's right up here. So we've got the 20.0 grams, and we multiply it by 100. Times 100, and it becomes 82%. So they were 82% effective at producing the calcium oxide. Any questions on these long problems? They are long. So on your test, are you going to have like 6 of these? No. You're probably going to have 1 or 2 of them. They're long. Or you may have parts of them, right? Like I may give you the actual and the theoretical and you solve for this, right? Or you just do this first part. It's not like you're going to get a top down, okay? Questions on where any of that's coming from? Or is that all like as we walk through it making sense? Okay, so you guys get to do one on your own. We'll see how much it makes sense then. That tends to be when you realize, didn't make as much sense as I thought. No, we're gonna do the other one. Yeah. Okay, so here is a problem. There's a balanced equation. It's a total crazy balanced equation, but don't worry too much. You don't need to use all the things. So where's the draw button over here? Okay, so we've got this big long equation. It says the starting substances are, you have 20 grams of the KAuCl4. So we know something about this. And it also says we have 25 grams of the Na2CO3. We have this. It says you are working towards the product AuOH3. So you're working towards this thing. All right. Which chemical is the limiting reactant? Which chemical is the excess reactant? So you have to like do the stoichiometry first to determine which ones those are. And I think the next problem 2 says how many grams, what's the theoretical yield? All 3 of these are going to be solved sort of together. So get started. I'm going to give you guys 10 minutes for this first part to work through it. And then we'll go over it. So it's going to model the same way that we did that last problem. You just have some new compounds and new formulas. Okay, so we want to get started. We'll use this 20 grams, so 20.00 grams of the KAuCl4. We want to convert that into moles. So for every 1 mole of KAuCl4, we get 377.9 grams. Now we want to work towards this. So we're going to use our ratios, and it's a 2-to-2 ratio. So 2 moles of the KAuCl4 yields 2 moles of the AuOH3. The last step is to convert that back into grams. So for every 1 mole of the AuOH3, it's 247.98 grams of AuOH3. Grams cancel, moles cancel, moles cancel. We get the value of 20 times 13.12 grams AuOH3. So now we get to do that same thing for the other one, right? So I've got 25.00 grams of the Na2CO3. We need to convert that into moles. So 1 mole of Na2CO3 equivalent to 105.98 grams. All right, and then the relationship between that and that is 3 of these for every 2 of these. So 3 moles of the Na2CO3 is going to yield 2 moles of the AuOH3. And then lastly, convert that back into grams. And fortunately, we've got the number from up here. So 247.98 grams of the AuOH3 for every 1 mole of that. Cancels all the way down, and we get 25 times the 2 times the 247.98 divided by 105.9 divided by 3. We get 39.03 grams. So what is our limiting reactant? What is holding the equation back? KAuCl4. This is the limiting reactant. What is the excess reactant? This, the Na2CO3. We'll have more than enough of that to run the equation. What is the theoretical yield? The theoretical yield is the number produced with the limiting reactant, 13.12 grams of AuOH3. That's how much we can produce in theory. All right, let's, I'm gonna skip over this and this because I don't really test you on that, but I do wanna look at the bottom one here. Okay, so it says, what is the percent yield if 9.848 grams of AuOH3 is actually produced. I'll give you 2 minutes for that because that's not a very challenging one. Okay, so for this one, percent yield equals our actual over theoretical times 100. Pretty simple. So we take the 9.848 divided by the theoretical, which is what you solved stoichiometrically, the 13.12, and we multiply that whole thing by 100. We get 9.848. 70, 266, so 75.06%. Cool. All right, I'm not doing another one of those examples because they take forever, but your homework will have some practice, so you can get more practice that way. But you know, if you've got these notes available for you while you're going through the test, use them as a guide to solve the problems. One more thing that I need to talk about is enthalpy. It's just a little add-on to stoichiometry. So enthalpy measures is a measured value of the amount of heat either given off or absorbed in a reaction. Turkey, stop. So we've got exothermic reactions, which emit heat, and then we have endothermic reactions, which absorb heat. The amount of thermal energy emitted or absorbed by a given chemical reaction under constant pressure conditions, which we will consider that everything we're dealing with is under constant pressure, can be quantified with a function called enthalpy. We define enthalpy of a reaction, or delta H of reaction, as the amount of thermal energy or heat that flows when a reaction occurs at a constant pressure. The sign on the delta H is important, whether it's positive or negative. So a negative sign means that energy is flowing out of the system, or it's an exothermic reaction. If you see a negative sign, you know that it's releasing heat. If it's a positive sign, it's an endothermic reaction. It means energy is moving into the system. So we've seen this chart before, but in an exothermic reaction, reactants have a higher amount of energy than the products. So to go from the reactant to the product, you have to lose energy. In an endothermic reaction, reactants have lower energy than the products, meaning you have to gain energy to get to the height of, or the new energy state of the products. So here's an example of a delta H of reaction for the combustion of methane. So every time we run through this problem, or through this reaction, this is the amount of kilojoules that are produced. Now, this magnitude of kilojoules is related directly to the moles of each of the different amounts. So if I combust 1 mole of methane, this is how much energy is produced. If I use 2 moles of oxygen, this is how much energy is produced. If I want to produce 1 mole of CO2, this is the energy produced. If I want to produce 2 moles of water, this is the energy that's produced. So there's a mole, just like the moles were related to each other, those moles are also related to this number. So we can go between the moles of a certain amount and the amount of energy that would get produced. Here's an example of an endothermic reaction. Positive sign, letting us know that it is absorbing energy. Again, this is a mole relationship. So for every 1 mole of N2, that combines with 1 mole of O2 and produces 2 moles of this, this is the amount of energy needed in order to do that. So we can use those amounts and a balanced equation to determine the delta H of reaction. So let's see, got it here. What's the problem? All right, so we've got propane here, the combustion of propane. So every time you run through this equation, you get this amount of energy produced. Well, let's say how to find out how much heat is emitted during a certain combustion of a certain amount of mass of methane. So if we know the mass of methane, we can convert that into moles, right? And then we know the molar relationship. 1 mole of methane will produce this much energy. Where is that? Well, this is for methane. So we would be using this one here. 1 mole of this will produce this much energy. So that's a conversion factor. So we can go from grams into moles and then moles into amount of energy, or kilojoules. Let's look at this one here. So it says we've got a tank of propane that is 11.8 times 10 to the 3 grams of propane. Calculate the heat in kilojoules associated with the complete combustion of the whole tank. So if we want to burn all of this, how much energy can we get out of it? Well, looking at the equation, I know that this and this are related to each other. That 1 mole of propane, C3H8, will yield this much energy, negative 2,044 kilojoules, right? Built right in. We're given grams. So I need to first convert grams into moles, and then moles can get converted into energy. We're hopping 2 hops. So let's look at how they've got it set up here. So you have your grams of propane. We've got the 11.8 times 10 to the 3rd. We use the molar mass of propane to get it into moles. And then we use that ratio of 1 mole for that much energy to get it into kilojoules. It'll look something like this. Our initial value, divided by the molar mass times the energy relationship. And we end up with negative 5.47 times 10 to the 5th kilojoules. Don't get scared by the scientific notation. It's just a big number. You get a lot of energy. So I'm going to have you do one of these using this here. Okay, we're going to say that we're given that we have 19.4 grams of N2. I want you to find energy absorbed. I'll give you all 3-4 minutes for that. Okay, so we've got 19.4 grams. (19.4 grams of the N2 given, and we're trying to find energy. So we're going to go from grams of N2 into moles of N2 and moles of N2 into energy or kilojoules. Well, 19.4 grams of N2, for every 1 mole of N2, we get 28 grams of N2. Why is it 28? Diatomic. Then the relationship says that for every 1 mole of N2, 182.6 kilojoules is produced. Right, so the moles cancel and the grams cancel. This is kind of a nifty way of now going from a mass to an energy. 19.4 times the 182.6 divided by the 28, and we get 127 kilojoules of energy. Any questions on that? How to move from an amount to an energy? You would have to have, the energy would have to be given to you, right? I'm not expecting you to like make that up. That would be given to you. Yes, Michael, yes, the kilojoules would always be given to you. It would be, you'd have the equation and then you'd have that delta H of reaction sitting next to it or right underneath it. Because you can't do the problem without it. Any other questions on that last part? Okay, we're done. We did stoichiometry. Yeah, whoa, we're done. Okay, so that's chapter 8. Don't forget to do your test. Don't forget to get your assignments done per usual, but you guys have been really good about getting everything in. And then, then we're moving into the last quarter of the semester. We really have like 2 more weeks left and we'll be finished. So just push through this last little bit, get it done, and then you don't have to think about Chem 092 ever again. If you have any general questions, throw them out. If you have any personal questions, wait around.